Okay. They are on page, they're in 4.5. 4.4, yeah. So they are on page, so they're on page 317. What about, I don't know. Do you want to choose, or you want me to choose?
Yeah, you can choose.
That's a weird one. Looks like, I don't know. Haven't looked at it. So now is the time. Okay. So first I have to plug it in. And where is this going when x approaches infinity?
One.
Exactly. Where is this going when x approaches infinity?
Infinity.
Excellent. So we have this, one of the three powers, right? Infinity to 0, 0 to 0, and 1 to infinity. These are the most cumbersome. Sorry about that. And I don't even know where the phone is. I found it. Okay, so remember the first step is I have to name the function. So this is y equals 1 plus a over x. This is a, not 9. A raised to bx. Okay, so the reason why, remember, we have to have an equation. I cannot apply log to a quantity. So I can apply log to both sides of an equation. So that's why we have to name the function something. We normally name it y. In step number 2, we apply natural log. So natural log y on this side, bx times natural log of 1 plus a over x on the other side. Leave that alone. In step 3, we apply limit to both sides. So limit of natural log y, of course when x approaches infinity, must equal limit of this. Limit as x approaches infinity from bx times natural log 1 plus a over x. Now I test again. So you already told me that 1 plus a over x is going to 1. You already told me that. Where is natural log 1 going now?
Zero.
Excellent. Now let's analyze this piece. When x approaches infinity, where is this piece going?
Infinity.
Yes. So this is a huge progress from a power, indeterminate case, to a product. And we like the product. Well, the ones we like are 0 over 0 and infinity over infinity. These are the ones we like. But with this one, we don't dislike. Why? Because it's a simple manipulation of this, keeping it exactly the same, but a different shape. We cannot change natural log. Natural log has to stay where it is. Do not, because if you put it the denominator with a negative power, it will be a mess. So natural log, leave it alone. But now I will change this into 1 over bx. How come? Is this the same? Yeah. This divided by a fraction is this multiplied by the multiplicative inverse of the fraction. So this function is the same with this function. But now I removed this type of indeterminate case. The numerator now is 0, and the denominator now is also 0. So this is not a bad case. These are the worst. These are the best. This is not difficult, I would say. It's not a bad one. Okay? And the last one that we know is infinity minus infinity, which depends on the function. But these are all 7. 2 we like, 1 we really don't dislike, maybe 2 we don't dislike, and these, Good. So now, do we all understand how we manipulated this to become this and have 0 over 0? Do we understand that step, everyone? Yes? Do I continue?
Yes.
Okay. Good. So now we can apply L'Hopital's rule. Only now we can apply L'Hopital's rule. So limit Sx approaches infinity. Remember how to differentiate natural log. 1 over this whole thing times the inner function prime. Very careful. 1 prime is 0, but this is negative a over x squared. Everything over. You can think of this, and I want you to, as 1 over b times 1 over x, please. So 1 over b stays alone by itself. It's a factor, waiting patiently. When I differentiate this, I get negative, of course in parentheses. I'm sorry, I didn't mean to, this has to be correctly the same row. 1 over x squared. So I'm gonna, so all fraction lines have to be on the same row, not above, below, no. Okay. So in the next step, I look and see, very nice. I will move a outside, and negative 1 over x squared and negative 1 over x squared will go away. But I have to move a outside. It's a factor. So I can do this. So limit as x approaches infinity. The denominator is 1 over b. So now this is a over 1 plus a over x. I divide 2 fractions, copying the fraction from the top and flipping the fraction from the denominator. Okay, finally, I have limit of ab over 1 plus a over x as x approaches infinity. What do we get? AB, very good. Excellent. At this point, we reached step 4. In step 4, I copy the beginning of step 3, and I copy the end of step 3. So I have that limit of natural log of y as x approaches infinity equals ab. Under continuity, I can move this operator in front and move this operator next to the function. So natural log of the limit as x approaches infinity from the function 1 plus a over x raised to bx equals ab. So now, as the final step, I have natural log of blah 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 equals ab. How do I solve this? In the following way. I write e raised to this power equals this. E raised to this power equals this. So, limit as x approaches infinity, 1 plus a over x raised to bx equals e raised to ab. All this has to be e to ab. Natural log of e to ab goes in front, natural log e is 1. Any questions? Any questions? So what we have left is row or mean value theorem or a problem in which we are given blah, 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 graph an example. Graph a function with blah, 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 blah given to us. Any questions? So what would you like to continue with? Anyone?
Would you mind doing a problem with the mean value theorem?
Absolutely not. Let's choose. My pleasure. Mean value theorem. This is in section 4.2. Here it is, 4.2, the mean value theorem. Okay. So, let's look at 17 on 296. We have f of x. Did we work on this problem? If we did, we'll choose another. So this is one option. 18 is another option. F of x equals 1 over x on 1 comma 3. I'll let you choose. Any preference? No preference?
18.
18, very good. So in number 1, on the interval 1 comma 3, I have to write that f is continuous on 1 comma 3. Guaranteed. It's not continuous at 0. But 0 is not here. I don't even have to write that. In number 2, because I know the graph, I know that f is differentiable on, and please remember this has to be an open 1 comma 3. Then I will say, by the mean value theorem, there exists a c in the open interval 1 comma 3 such that f prime of c equals f of 3 minus f of 1, the slope of this line going through those two, 3 minus 1. I have to find f prime of x. So f prime of x, as we know, is negative 1 over x squared. I have to write this equation. Plugging in c, negative 1 over c squared equals f of 3 is 1/3. F of 1 is 1. 3 minus 1 is 2. I have to solve this for c. And I also have to show that is in the open interval 1, 3. Not only solve it, but also show that the number I get is a number between 1 and 3. So I have to solve the equation for c. It's quadratic, so I have to show 2 solutions. Then I will have to say either both are here or just one, and I will select the one that is guaranteed by MVT. So let's solve this algebraic thing here. Okay, so 1/3 minus 1 is negative 2/3 over 2 over 1. Negative 1 over c squared equals negative 2 over 3 times 1 over 2. Negative 1 over c squared equals negative 1 over 3. From here, multiply both sides and flip. I know that c squared equals 3. And I have to take the square root. I have to write that c equals plus or minus the square root of 3. But because the interval is 1, 3, I will say no. Only c equals the square root of 3 is in the interval 1, 3. Only this is guaranteed by MVT. So not only that I have to find correctly 2 solutions because it's quadratic, but also when I'm done, I have to say, yes, this one fits, the other one does not. Good. Anything else? Anything else?
Yeah, in case anybody doesn't mind, I have a weather sign problem I had issues with.
Yes, I'm ready.
So I think that was the graphing.
Yes, I'm ready.
I think that's 4.6 problem number 2.
Is it from Weber sign?
Yeah.
Can you read the function for us?
All right. So they said produce graphs of f that reveal the important aspects of the curve, and f of x is given as 5 sine x.
You said sine x?
Yes. Plus cot x. And the interval is given between negative 5 and pi.
Negative 5, 5? Negative pi, pi?
Negative pi and pi.
Yeah, that's
So
what I
x is-
thought.
Yeah.
Okay, so let me read this one more time. Is it 5 sine x plus cosine x?
Yeah.
5 here?
Yeah, that's it.
Okay. And we're asked to graph?
Exactly what I was to graph.
Okay, perfect. Okay, another messy one. at negative pi, this is 0, this is negative 1. So it's going to be negative 1. At pi, this is 0, this is 1. This is negative 1 as well, sorry. So at pi, again, this is 0, this is negative 1. At negative pi, still 0, still negative 1. When x is 0, this is 0, and this is 1. Okay. Does it have other solutions?